In this video, we're working an example of a Bainbridge mass spectrometer. And I made a larger video about the design and operation of a mass spectrometer like this, and I'll post a link to that real quick. But let's review the basic design real quick. The point of this device is that you can figure out the masses of all the atoms and molecules and fragments of molecules in a sample by first ionizing that sample. So we take a sample and we vaporize it. Then we hit it with high energy electrons to ionize the particles in that sample. That means we're knocking electrons off those particles. For the most part, those particles end up singly ionized, meaning they're missing one electron. There will be some double ionization events, and you'll see that in your data, but it's rare compared to the single ionizations. So we have a bunch of positively charged particles now that came from our sample. We push them out of the sample container with a positively charged plate called the ion repeller. That gets us into an accelerating potential where we accelerate those positive ions from a high potential to a low potential to speed them up. We fine-tune the velocity of this beam of particles by passing through a speed selector, and that's constructed by crossing electric and magnetic fields so that only one special speed is allowed to pass through that filter. Now we have a narrow beam with a very narrow range of velocities entering what's called the analyzer region of the mass spectrometer. And the point of this region is to bend the path of those charged particles until they land on a detector. Now the radius of curvature of those particles depends on their mass, and so knowing all the parameters in this mass spectrometer, you're able to calculate the mass of the particles hitting the detector. So in practice, this mass spectrometer is going to sweep through a bunch of different settings. You can catch particles of different masses by tweaking the strength of the magnetic field in the analyzer region. You can change the accelerating potential if you need to explore a different regime of velocities. You can fine-tune those velocities by changing electric and magnetic fields in the speed selector. So by sweeping through different settings in this mass spectrometer, you can catch the masses of all the different species that are in your sample. In this particular example, we're just looking at a nitrogen-14 atom that's been singly ionized. That means it's missing one electron, so it has a charge of plus QE, plus 1 elementary charge, or 1.6 times 10 to the negative 19 coulombs. And we're exploring some of the settings in the mass spectrometer to get a better understanding of how it works. So in part A, I'm asking, what's the accelerating potential required so that the ion has a final speed of 3.5 times 10 to the 5th meters per second before it gets to the speed selector? And so I have a nitrogen-14 ion that ends up entering the region of the accelerating potential, and it's going to move from high to low potential. And the speed at the end of that process is determined by an energy conservation calculation. And the change in potential energy of a charged particle is given by Q delta V, where delta V is the potential difference. And the magnitude of that potential energy change, well, that turns into the kinetic energy of that particle. Now, the magnitude of the change in voltage is just capital V because the potential of the other plate is 0. So I end up with a QV, capital V for the voltage. It's equal to 1/2 mv squared. And the way this particular problem is set up, I'm trying to calculate the accelerating potential corresponding to a known speed. So we solve for V, and I get mv squared over 2q. So if we just plug in the mass, the desired speed, the charge on these ions, I should be able to get the required accelerating potential. There's a little bit of prep work that has to be done because we were given the mass of this ion in atomic mass units. 14.003 atomic mass units. I have to multiply by a conversion factor here. There are 1.66 times 10 to the negative 27 kilograms in an atomic mass unit. And when I run the numbers on this, I get a mass of 2.324 times 10 to the negative 26 kilograms. So we're ready to plug in our numbers. And I put that mass in there, 2.324 times 10 to the negative 26. The speed of our particle beam is 3.5 times 10 to the 5th meters per second. And then the charge on these singly ionized nitrogen-14 atoms is 1.60 times 10 to the negative 19 coulombs. When I run the numbers on this and round to 3 significant digits, I get 8,900 volts. So an accelerating potential of 8,900 volts would cause nitrogen-14 atoms in particular to be moving with this speed of 3.5 times 10 to the 5th meters per second. If our speed selector is set to that value, We get a very narrow range of velocities in this particle beam entering the analyzer region. In part B, we want to determine what magnetic field strength would actually cause these particles to hit the detector. And when we get to this special magnetic field strength, we're going to register a current in the machine because we have all these positive particles hitting a detector that's part of a larger detection circuit. So first, we're told the detector is 35 centimeters from the point of entry. And this means the radius of curvature of this particle beam is half that. That's 17.5 centimeters. Or I could say the radius of curvature is 0.175 meters. And these nitrogen ions are moving in cyclotron motion. So that's the motion of a charged particle curved into a circular path in a magnetic field. There's the velocity vector for one of these particles, always perpendicular to the trajectory. And when I apply the right-hand rule for the Lorentz force law, I can take my fingers in the direction of V, sweep out to the direction of B, and my thumb points in the direction of the magnetic force. Well, that's perpendicular to V and pointing to the center of curvature. And there's our center pointing force that causes circular motion. When we do a force analysis on this, it goes back all the way to Newton's second law, F net equals ma. And the force experienced by this ion is the Lorentz force, and that's QVB times the sine of theta, where theta is the angle between the velocity vector and the magnetic field. Well, that's just 90 degrees because the velocity is in the plane of the page and the field points out of the page. And the sine of 90 degrees is 1. Our acceleration is related to the speed and the radius of curvature by v squared over r. And now we should be able to solve for the magnetic field corresponding to this radius of curvature. So we cancel one factor of r and isolate b on the left-hand side. And b is going to be mv over qr. We plug in our numbers. And when we round to 3 significant digits, we get 0.291 Teslas. So if we imagine what this looks like in practice, you can set up a narrow beam of positively charged particles, fine-tune the speed distribution very closely around 3.5 times 10 to the 5th meters per second, and then sweep through a bunch of different strengths of magnetic fields just by turning a knob. When you hit 0.219 Teslas, you're going to detect a current in this mass spectrometer, and you can quickly compute the mass of that particular species. This contributes a line to the mass spectrum of your sample, and you can say you detected nitrogen-14 in your sample. You continue to sweep through different settings on the mass spectrometer, and you can find a bunch of lines corresponding to the masses of all the different atoms, molecules, and fragments of molecules in your sample. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.